In the sequential, remember that this was our case where we had this, PC, right? In this case, you would feed into instruction memory, and then we would get these, values. Remember, like these values were not intermediate values. We were just post-its that we had stick around the cables. And this would go as such, okay, memory, and then write backstage here, and then PC, and then after this, then everything would move back. Okay, this is our this was our sequential design. Now we will make a slight change here, okay, which we call sequential plus. When I was staying at my house, we had this we would cook in the kitchen, right? So cook in the kitchen was like this. So you start you have this the nice thing you cook, and then you would eat. You wash the dishes. Does it work? The reality was quite different. Whenever I would go to the kitchen, dishes were always dirty. So if you want to cook, you would start it by washing the dishes first, and then cook, and then you eat, and then let the dirty dishes stay there for the next guy. You can see that these are equivalent. You just do exactly the same things, except that you have this slight difference, right? So we will rearrange the sequential processor in this manner, meaning that it's exactly the same thing, except that instead of doing the washing at the end, we will do the washing at the beginning. Now let's go back here. Now in this sequential hardware, the last thing that we compute was the new PC. And in this case, the new PC was computed by for different cases. Like I said, the next one, right in the sequence, it can be if it's a jump condition, then we look at that. It can be a call or return. Okay, but what you do is at the end you compute the new PC. This is what you would. Okay, this would be coming here, and then you would store it here in the PC. That's the idea. So how do we compute this new PC? If you look at our code, again, you should go back to that. And this new PC, this would come out of a box, control box. And into this box, then we would feed in a lot of different signals. Val C, maybe, val E, maybe, condition, I code, I find. And you would use them to compute the new PC such that you get ready. That's how the sequential processor works. Now, what I will do in sequential plus is I will not compute this new PC here, but instead I will store them, use them as my beginning. Remember, in this case, I had this PC, correct? So what I would do is I would from this, I would compute this PC and I would feed this in here. Now, in the sequential plus, what I would do is, at the end of my cycle, I would compute all these values and I would store them. So this is the previous instructions, I code, condition, val M, val C, and val P. So I would store them at the end, like at the end of each of them. And then when with the rising edge, what I would do is I would compute the PC as a signal. So this one is not a register. I don't have a PC register. This one is a control box. And what you would do is, at the end of every instruction, you would compute these instructions, I code, etc. When the rising edge comes, what you do is you compute the PC as a signal and then feed this to your instruction memory. So in sequential plus, I don't have a PC register. Rather, I compute PC using the signals that I have computed in my previous instruction. This is a little bit hard to swallow, but actually the same thing. What I do is, I start by washing. I start by washing the dishes that were dirty by the previous guy. So in this case, you can see that, the PC is no longer stored in a register, but I can, determine PC based on the previous instruction here. So this was the sequential one. And what I would also do is I would insert pipeline registers. And these registers that I have here, for example, for the fetch stage, the pipeline registers What you can also do is the previous I code is stored in here. Previous maybe iPhone or previous val p. So I would store them in my, these are all pipeline registers, okay, in here. I would store them, and now this means that all I have to do is for my signal to go start from here and to go all the way to there. So that requires a much shorter clock signal. Are you still with me? I know this is a little bit tough to digest, but I think we will be able to do this. The way it works is, again, we have these pipeline stages, right? Fetch, decode, execute, memory, and write back. And what we don't is we don't have the PC stage because we kind of eliminated PC stage by not requiring any PC computation. And when you look at them, they do exactly what we were designed to this. Now, the main difference between the sequential processor and the pipeline-based version is that in here I have discrete steps. I store the results of these values, okay, in these registers. In the sequential processor, all the signals that I had, that I was computing, they were all kind of like live on the wires. I never have stored them. For example, think of val A. The val A was never stored in a register. Instead, val A was just, it appears on some of the wires, but eventually when you look at the registers, it never appears. Whereas in the pipeline case, now I will have val A. For example, let me just look at here. So this is my fetch stage, right? So we have seen this, we have this, previous I code, etc. Now, in the decode stage here, okay, what do I have? This is in this case, I will have the partially computed results. What are the partially computed results after the fetch stage? I code. Then I can have my iPhone, RA, RB, val C, etc. Then I store these intermediate results into the pipeline register at this. What about here? In this case, I will copy some of the I code and iPhone. Okay, this will be useful later. I pass them. But in addition to this, I will also add val A and val B here because now I'm adding more partially computed results. And for example, when I get to here in my pipeline register, remember what I'm doing is as I move on, I pass and I store the values that are partially that I need to pass to the next stage, the partially computed ones. For example, here maybe I will be the condition signal. I need that, okay, or maybe val E. Val E has appeared, and etc. So this is how it would work, and in this case, all these stages, this is discrete. In the previous skill, like in sequential processor design, we had split them into these discrete stages, whereas in actual reality, it was not discrete. It was just signals propagating through the combination circuit, whereas here, I have actually split them up into these by these registers, and these stages are now discrete. So let's call this, look at these basically details here, which we call pipe minus hardware. Okay, in this case, note that these pipeline registers, they hold the intermediate values from the instruction execution. Okay, and we will have them, forward paths where the values are passed from the next one. Okay, you cannot jump past stages. Here's my stages. For example, for the D stage, I had the I code, plus other things like stat iPhone, okay, RA, RB, val C, and in this stage, I also compute val P, for example. So I also store this because I will need this. And after the decode stage, okay, some of these, the code, for example, they are moved on to the next stage. You're just passing that. But for example, what we will do is we will pass on, for example, val A and val B. Okay, these are the new guys, right? Because I have accessed my register file. Okay, now you pass them in here, and then when you move on to the next stage, then you can see that condition appear here, val E appears here, okay, val A appears here, etc. And some of them I may be dropping. For example, iPhone, okay, I use this here, but maybe this iPhone is no longer valid after I complete my condition signal, right? So I no longer have to state this. I just, discard it. Okay, so you just pass only the signals to the next stage, such that the next stage can carry out its computation.